Hey everyone. Today we're going to be starting our last lesson in Unit 7, covering percent composition and molecular formulas. Two kind of short, quick topics. And as we finish this last lesson here in Unit 7, our full first unit using the flipped classroom, on the back of your notepad, I'd like you to answer the two questions or provide the following two pieces of information listed here. So at the back of your notepad, I'd like you to give two reasons why you would want to continue learning with the flipped classroom. And then I'd also like you to provide two reasons why you do not want to continue learning with the flipped classroom. We'll see kind of what you come up with when you're back in class, and we'll discuss if this is something we want to continue trying, or if it's something that we'll forego doing for now, and we'll look into maybe going back to our traditional learning environment, or maybe we'll try something else. Onwards and upwards. Percent composition. You guys are probably somewhat familiar with this, although you might not think of it as percent composition. But we use this a fair amount. In chemistry, really what this is a simple, really just a proportion by mass when we consider the different types of elements that are in a compound. And this is a form of quantitative analysis that's going to give us numerical data on how much of each element is in a compound. It's how we come up with our ratios in a compound like CO2. Within that entire molecule, 2 oxygens, 1 carbon, what would the total percentage of carbon be in the compound? So to do this, we weigh a sample of a compound, take the compound and break it down, decompose it into its individual elements, into carbon and into 2 oxygen. We then weigh the masses of carbon and oxygen, and we can calculate the percent by mass of each of those elements in that compound. But what we need to know is how much the total is and how much each of the parts are. Sometimes all we need to do is calculate the percent of each element in the entire sample. So to do this, we're going to use a simple formula, and this is at least in some form of the equation that's given to you on table T. And in simple forms, we've used this in lab a couple times this year. In real simple form, to find percent composition, it's always part over whole times 100. This is how we would find how many correct answers you got on a test. If the test has 100 questions, that's your whole, and you got 90 of them right, we get a percent composition of correct answers is 90%. We could do that with how many you got wrong. 10 over 100 times 100. Our percent wrong is 10 over 100, or 10%. Here's an example. The compound containing nitrogen and oxygen has a mass of 80 grams, 80 total. Experiments show that the 80 grams is made up of 56 grams of oxygen and 24 grams of nitrogen. What is the percent composition by mass, so we're dealing with mass here, of each element in the compound? So we take the whole, which the whole of the compound is 80 grams, that contains nitrogen and oxygen, and we can calculate each part. So we have 56 grams of oxygen, so that could be one part that we can look at, and we can look at 24 grams of nitrogen. So for each one, we use the part over the whole. The part in this case for oxygen is 56 grams divided by the total of 80 times 100. which is 70%. So 56 is 70% of 80. For nitrogen, we do the same thing using the part of nitrogen as 24 grams over the whole of the compound of 80 grams, which gives us a percent composition of nitrogen at 30%. So 24 is 30% of 80. Sometimes some of these numbers are nice. Sometimes we're going to have to look information up on the periodic table. For example, if we're just given a formula and we want to find the percent composition by mass of each element in a particular compound. Before we do that, we first need to know what the total is, or what the whole is, of the compound, in this case silicon dioxide. So we have to find the gram formula mass of silicon dioxide. So silicon weighs 28.1 grams per mole, oxygen 16.0 grams per mole, and if we have two of those, that's a total of 32 grams per mole. We add these together and we get a total formula mass of 60.1 grams per mole. Now that we have the whole, we can figure out what the part is. We had one silicon in our formula. Each silicon weighs 28.1 grams per mole. We divide that by the whole of 60.1 and we get a total of 46.8%. So that one silicon in SiO2 contributes almost 47% of the mass of the entire compound. To find oxygen, we take all of the oxygen, not just one, but both, because two atoms are contributing to the mass of that compound. So we take the total of 32 grams per mole and divide it by the whole of 60.1, multiply it by 100, and we get a percentage of 53.2%. We could also just kind of take this and say, okay, 46.8, and we can subtract this and get 53.2. But I think it's important to actually be able to calculate that both ways. Then we can just verify the numbers as a check in that regard. We're going to do a lab determining how much water is in a hydrate. And a hydrate is a compound that has water that is part of its molecular structure. We might see something like this. Take a second, you can name that. It is calcium hydroxide. We might see this added onto a formula. It looks like the multiplication symbol with a number followed by H2O. This tells us that when we see this multiplication sign here in our formula, it's telling us that within one of these molecules of calcium hydroxide, there are 5 water molecules that are kind of encrusted as part of the formula, as part of the structure of calcium hydroxide. And if we heat that compound, we can heat out the water, get rid of the water, which would essentially lower the mass of the remaining compound. We're going to do a lab on this. And the way we'll do that is we'll take the mass of the original hydrate, whichever one I give you, which is actually going to be an unknown. We heat it until it's long enough where we believe all the water is gone out of the hydrate. We mass it again, and then we figure that the difference there from the initial mass to the mass after heating is due to the water that's being evaporated. And then we'll figure out the percent of water using pretty much the same idea here. Part over the whole, mass of the water over mass of the hydrate. The hydrate being the original crystal that had the water in it. The mass of water is the difference that was heated out between the hydrate and the anhydrate. We multiply that by 100 and we'll get a percent of water. For example, a 10.4 gram sample of a hydrated crystal is heated to a constant mass of 8.72 grams. When you see that constant mass, that means as we continue to heat, no more mass is being lost. So we can assume that the compound is dry and there's no more water in there. So all the water has been driven out by the heat. We figure out what the mass of water was that was driven out by heating. So we take the hydrate and subtract the mass of the anhydride, which is the remaining compound without water. So we subtract 10.4 minus 8.72 grams, and we can figure out how much water was driven off. This 1.68 grams is our part. That's the part of water. So to figure out the mass, or the percent by mass of water, we're going to use that part of 1.68 grams and divide it by the mass of the entire hydrate, 10.40 grams. We do that, we multiply by 100, and we get a figure of 16.2% water by mass. So in that original 10.4 gram sample, since we lost 1.68 grams, 1.68 grams is 16.2% of the 10.4 gram sample. So that sample from beginning to end lost 16.2% of its mass. You can kind of think of this like a piece of fruit that's left out and left to dry over a couple weeks period. It just kind of loses all of its water and all of its mass. It's true for fruits and vegetables. A lot of the mass is water. Think of watermelon. I think watermelon is something like 80% water. So if you leave watermelon out to dry for a couple weeks, you'll be left with 20% of the original weight. Don't quote me on that figure. Sometimes this is a little bit harder. What's the percent composition by mass of each element in CuCO3? I'll give you a chance to name that. Copper carbonate. And again, we see that multiplication symbol here indicating that this is a hydrate and it has two water molecules encrusted into its crystal structure. So that is a hydrate. So we got to figure out the formula mass of that entire thing, and we do need to include all of the waters. So when we look at this, we have one copper, we have one carbon, we have 3 oxygens here, but we also have 2 oxygens here, and this 2 to 2 we have 4 total hydrogens. So we factor those numbers in when we figure out our formula mass. We get a figure of 159.5 grams per mole. So the 5 oxygens, we got the 3, as I said, in copper carbonate, and there's 2 more in the 2 water molecules. So to figure this out, we use the formula mass of the entire compound, 159.5 grams per mole, and we can now take the mass of each part, each element in there, and determine the percent composition of each element. We only had 1 carbon, so we use the 12 gram per mole value over the total. And we can see from this that most of our mass is coming from the oxygens, 3 from the copper carbonate and 2 more from the water itself. Very small percentage is hydrogen. Alright, at this point you should be able to determine the percent composition of an element in a compound and determine the percent composition of water in a hydrate. You have the information of how to do it, you have the notes of how to do it. We'll soon be doing some practice with that. A little bit on empirical and molecular formulas and how it relates to percent composition. Now we learned prior that the empirical formula is the simplest ratio by mole of any element in a compound, meaning we can't simplify it any further. It's already in simplest forms. So HO shows a 1-to-1 ratio of hydrogen for every 1 oxygen. That can't be simplified any further. Now molecular formula is simply a whole number multiple of an empirical formula. So hydrogen peroxide's formula is H2O2. That's a 2 hydrogen to 2 oxygen, or a 2-to-2 ratio. But we can simplify that. We can divide out at 2, and we'd be left with an empirical formula of 1-to-1, a ratio of 1 hydrogen to 1 oxygen. So H2O2 is a molecular formula and a multiple of 2 of the empirical formula HO. So the molecular formula is twice the size and therefore twice the mass of the empirical formula. So the empirical formula CH2, which we'll get into a lot more when we get into organic, has a few different molecular formulas. CH2 by itself, as the empirical form, has a formula mass of 14, 12 from the carbon and 2 from 2 hydrogens. If we multiply that by 2, not only we do double our mass here from 14 to 28, but we double the number of elements that are in the formula. And we're basically just kind of multiplying the 3 across the C and the H. And each time we are adding the empirical formula mass of 14 each time to our molecular formula. But even at C5H10, this is still a 5 to 10 ratio or a 1 to 2 ratio, which we see in the original empirical formula. So determining molecular formula from mass and empirical formula. So as long as we have a few pieces of information, we can figure out what a substance's molecular formula is. So first thing we want to do is determine the formula mass of the empirical formula and divide the molecular mass by the empirical mass. This gives us a whole number multiple. So it's got to be a whole number. It doesn't have to be necessarily, but that's what we deal with in Regents chemistry. That'll tell you how many times larger the molecular formula is than the empirical formula. We then just take that whole number multiplier like we saw on the previous slide and multiply it across the empirical formula, and it will give us the molecular formula. Of course, I'll show you an example of this. So we have an empirical formula of a compound is C2H3. We cannot simplify that any further. And the molecular mass is 54 grams per mole. What is the molecular formula? So first we'll figure out what the formula mass of the empirical formula is. We have 2 carbons and 3 hydrogens. That comes out to 27 grams per mole. In general, we'll see this as pretty nice numbers because we have to get a whole number multiple. So we divide the molecular mass of 54 grams per mole by the empirical mass, 27 grams per mole, to get our whole number multiplier. And that'll tell us how many times larger the molecular formula is than the empirical formula. And in this case, it is 2 times larger. So we multiply that whole number multiplier by the empirical formula of C2H3, and we get our molecular formula, C4H6. Note that this still maintains the 2 to 3 ratio. Another example here. What is the molecular formula of a compound whose empirical formula is CH with a molecular mass of 52? So we start with the formula mass of the empirical formula, CH, which would be 1 carbon, 1 hydrogen for a total of 13 grams per mole. That's our formula mass. We'll divide the molecular mass of 52 by the mass of the empirical formula to get our whole number multiplier. In this case, it is 4 times as large. So we'll multiply that 4 across the CH in order to figure out what our formula is. In this case, C4H4. And that would be our molecular formula for that compound. We will be doing lots of practice with this in class. Please write down any questions that you have. And don't forget to write down your 2 points for or against for continuing with the flipped classroom. I'll leave you today with a joke. The optimist sees the glass half full. The pessimist sees the glass half empty. But how does the chemist see it? Completely full. Half with liquid and half with air. Have a great day, everyone.